Welcome to this topic of the Demystifying IPv6 course on IP version 4, IP version 6 transition. This particular topic is broken up into two parts, and this is part 1. So transition mechanisms have been discussed for many years regarding the migration from IP version 4 to IP version 6. There's a lot of different strategies that have been devised, some of them just ideas and never implemented, some of them only temporarily implemented, and then some newer strategies that are in use today. We'll cover a variety of those in this topic and the next, but it is very confusing because you'll see references to old things that were just ideas or used at one time and not used again. In this particular topic, we'll definitely cover the dual stack IP layer, the DNS infrastructure, and we'll start our discussion of IP version 6 over IP version 4 tunneling. But the second topic will also get into more specific examples of that, such as the most current strategy, 6RD and DS-Lite, as well as compatibility addressing formats and translational mechanisms. So dual stack was defined by RFC 4213, and the idea is the nodes would actually be running two different stacks, one for IP version 4 and one for IP version 6, and then depending on what application and protocol they were using, they would just use one stack or the other. It's actually the most widely spread use of IP version 4 to IP version 6 transition because it doesn't require any tunneling or translational methods. Of course, it does require all the infrastructure, including the DNS resolvers, to support both IP version 4 and IP version 6 mechanisms. The idea of the dual stack architecture is to have a separate TCP and UDP and therefore IP version 4 and IP version 6 implementation. However, it is a little misleading because most implementations do not actually offer two completely distinct TCP IP stacks, one for IP version 4 and a separate one for IP version 6, but rather they have some form of a hybrid stack in which most of the code is shared between the two protocol suites. The DNS infrastructure is needed for successful coexistence because of the prevalent use of names rather than addresses to refer to network resources. Of course, this is even more true with IP version 6 as we discussed in the addressing architecture, where the numbers could actually be 128 bits long. So upgrading the DNS infrastructure consists of populating DNS servers with records to support IP version 6 name to address and address to name resolutions. After the addresses are obtained using DNS, the sending node must select which address to use for communication. The idea is you could send a DNS request for a specific name and actually receive back both an IP version 4 and an IP version 6, or possibly even many flavors of IP version 6 addresses, as we talked about earlier with scoped addresses, that you might have multiple IP version 6 unique addresses to select from. So a new resource record type named Quad A has been defined for IPv6 addresses in RFC 3596. So the DNS infrastructure must contain the following resource records for the successful resolution of domain names when migrating from IP version 4 to IP version 6. Of course, you have the original A records for IP version 4 addresses and Quad A records now for IP version 6 addresses. For reverse lookups, there is a new ARPA record, the ARPA domain, that has been added for IP version 6 addresses as well. And as I mentioned, what if you get back multiple addresses, either a combination of IP version 4 and IP version 6 or multiple IPv6 addresses? So RFC 3484 was written to address that. As you can see in this slide, typically by default, IP version 6 addresses in the DNS query responses are preferred over IP version 4 addresses. So now that we've covered dual stack and the DNS infrastructure, we're going to take a closer look at tunneling. The idea of tunneling is to encapsulate IP version 6 packets in IP version 4 packets for transport over existing IP version 4 either intranets or even the global IP version 4 internet. Yes, it might surprise you to know that today there is a lot of IP version 6 traffic that's traversing the global IP version 4 internet, though that is considered an interim solution until everybody has global connectivity over a native IP version 6 internet. The idea with encapsulation is you set the IPv4 protocol field to 41, and that indicates that the next layer protocol is actually IPv6. And then you have your IPv6 packet inside of the IPv4. Of course, ultimately on top of IPv6 packet, you're going to have UDP or TCP and then application data. The idea of tunneling also means that the IP version 4 address is actually embedded in the IP version 6 address, so the source and destination of the tunnel endpoints can determine what is the appropriate IP version 4 addresses to populate in the IP version 4 tunnel. Tunnel endpoints are either manually or automatically configured, and we'll cover more on that in subsequent slides. So this slide provides an example of IP version 6 tunneling over IP version 4. In this slide, the big cloud in the middle is, let's consider the global IP version 4 internet. And the two hosts on each side are on native IP version 6 links. And so the routers that they're connected to locally are running natively IP version 6. And so each host just sends an IP version 6 address as it normally would, thinking that they have connectivity between each other over a pure IP version 6 internet or intranet. So the idea then is the address that host 1 and host 2 are using have an embedded IP version 4 address if it's automatically tunneled, or if it's manually tunneled, then the IP version 4 address does not necessarily have to be embedded in the address. Routers A and B actually have a link to the IP version 6 link as well as IP version 4 links, and they're considered the tunnel endpoint. So the tunnel that we're going to build here is between A and B. So router A on the IP version 4 internet side has a globally unique IP version 4 address, and router B does too. So now host 1 wants to send an IP version 6 packet to host 2. Again, the two hosts just think they're using normal IP version 6 routing, and in fact the two routers that they're directly connected to think that way too. So host 1 just sends a normal IP version 6 packet with an IP version 6 header and payload. That is eventually received by router A, and router A interprets the destination IP version 6 address. So it looks at the destination IP version 6 address and extracts what would be the tunnel endpoint associated with router B from that, either manually because it's configured that way in router A, or automatically because the tunnel endpoints, i.e. the two IP version 4 addresses of router A and B, are embedded in the IP version 6 addresses. So the table in router A says for that destination of 2, use the tunnel endpoint of 163.101.18.5 and build that as a destination IP version 4 address once you encapsulate the IP version 6 packet in an IP version 4 packet. So router A encapsulates the IP version 6 within the IP version 4 packet. So now we have a packet where you have the original IP version 6 header and payload encapsulated inside of an IP version 4 packet, and notice the source and destination IP version 4 addresses are the tunnel endpoints of router A and B respectively. Of course, the packet sent from router A to router B follows normal IP version 4 routing through the IP version 4 internet in this example. And so again, there's a lot of IP version 6 traffic traversing the global IPv4 internet using this mechanism. Router B receives the packet and then strips off the IP version 4 header. the original IPv6 packet and payload are forwarded on to the IPv6 links that device 2 is connected to. And then it follows normal IPv6 routing to get to device 2. So this slide just gives you another example of the tunneling format. So you start out with the original IPv6 header, possibly any extension headers, and then upper layer protocol that is transmitted. And then ultimately it gets encapsulated with an IPv4 header where the protocol then is set to 41, which indicates that the next protocol header is an IPv6 header instead of, say, TCP or UDP. As you can imagine, since we're just adding another 20 bytes on with an IPv4 header, for largest packet size, you need to watch out for MTU or maximum transfer unit issues then. So regarding the path maximum transfer unit, one might assume that the IPv6 packets will not exceed the typical MTU of IPv4, especially since IPv6 has a default MTU of 1280 and most IP packets are carried over Ethernet links which have an MTU of up to 1500. However, since path MTU information is not stored for the tunnels, you have to make some accommodation for the fact that the packet could end up larger than an MTU of any particular link. As per RFC 4213, if the path MTU side is too large for some intermediate IP subnet, IPv4 fragment will ensue. While this is undesirable, it's not disastrable. So when encapsulating an IPv6 packet inside of IPv4, the do not fragment bit should not be set in the encapsulating IPv4 header. So as I mentioned earlier, there are two types of tunnels. There's configured tunnels and automatic tunnels. Under configured tunnels, the IPv4 address of the tunnel endpoints are not derived from embedded IPv4 addresses in IPv6 addresses, rather they are configured manually. The following are types of manual tunneling technologies: manual configured tunnels or generic routing encapsulated IPv4 tunnels. Automatic tunnels do not require manual configuration. The tunnel endpoints are automatically determined by looking at the source and destination IPv6 addresses having embedded IPv4 addresses. Embedded IPv4 addresses and IPv6 addresses are often referred to as compatibility addresses. The following are types of automatic tunneling technologies. There was a previous but obsolete mechanism called 6/4, which assumed that the IPv4 network that we were tunneling across supported multicast. And as we know, the global internet doesn't, and or a lot of intranets don't either. So that particular technique is obsolete. ISATAP we'll cover later, as well as 6/4, 6RD, and Torito are other examples of automatic tunneling technologies. Those will all be covered in the part 2 of this topic on IPv4, IPv6 transition strategies. The following slides are going to cover tunneling from a more generic standpoint. So I mentioned on the previous slide the idea of compatibility addresses, and those are those addresses where an IPv4 is in some way embedded into an IPv6 address. When we look at each of the protocols such as 6/4 and ISATAP and such later on part 2 of this, then you'll see more about just what that means. But notice that the 6/4 address has a 2002 prefix, and then the IPv4 address is actually the next 32 bits. So 16 plus 32 is 48. So the most significant 48 bits for 6/4 is a 2002 prefix followed by the 32 bits of the IPv4 address, and then followed by the subnet and eventually the interface ID of the end host. And so you can determine via the www.xxyyyzz what the source and destination of the IPv4 tunnel endpoints are, as was discussed on the tunneling example a couple slides ago. And you see similar mechanisms for the other protocols that use compatibility addresses, such as ISATAP, Intrasite Automatically Tunneling Address Protocol, and Torito, which is another mechanism for tunneling, but tunneling in the existence of NATs, where we need to run IPv6 over UDP IP. instead of encapsulated directly in IP version 4. So as I mentioned on the previous slide with Torido, there is a concept of NAT, network address translation, that we need to take into effect because NAT is very widespread with IP version 4 today, and in fact it's the only reason IP version 4 has lasted this long. So I mentioned earlier you have two types of tunnels, configured and automatic, but then there's also configured and automatic in the presence or absence of a NAT. So there basically translates to four different categories of tunnels. A few comments regarding tunnels to make here. Configured tunnels only operate point to point, whereas automatic tunnels can be point to multi-point. A couple examples of automatic tunnels in the absence of NAT is 6 to 4 and more currently 6RD. Again, we'll discuss those later on. Torido is an example of a solution for an automatic tunnel over IPv4 across a NAT environment. RFC 2893 was the main standard that defined transition mechanisms for IP version 6 hosts and routers. That has subsequently been obsoleted by RFC 4213. One of the things obsoleted was this concept of automatic tunneling. RFC 2893 had a concept of that, but a more general mechanism was written, RFC 3056, which defined the 6 to 4 mechanism. Although RFC 5569, which is 6RD or IP version 6 rapid deployment, is now preferred over 6 to 4, and we'll discuss more about that in the second part of this topic. So now RFC 4213 only defines dual IP layer and configured tunnels, so it has no reference to automatic tunnels anymore. It also defines node types and tunnel types. RFC 4213 defines the following types of tunnel configurations: router to router, host to router, router to host, and host to host. And depending on what you're trying to accomplish, if it's router to router, it generally means that you have one version of IP on the endpoints and another version in between. So as discussed a few slides ago, we had IP version 6 on both ends and IP version 4 in between. So we needed a router-router tunnel to get our IP version 6 traffic over the IP version 4. There's also circumstances where you might have IPv4 on the end and IP version 6 in the middle. And so we'll address that in the second part of this as well. Host to router and router to host means that the host is connected to one type of protocol but trying to run another over it. So instead of the host trying to send IP version 6 packets over a directly connected IP version 6 link, what if a host needs to send IP version 6 packets but it's only connected directly to an IP version 4 link? So host to router and router to host address that. With host to host, it's similar to host to router, but now both hosts are actually and generally on the same subnet as far as the IP version 6 protocol is concerned, but they're both connected directly to IP version 4 with no other tunneling required in between. One interesting note about tunnels is all the tunneling mechanisms, whether they're configured or automatic, there is no tunnel setup, maintenance, or termination. So the tunnels don't need to be signaled, such as this case with MPLS. And none of the tunneling techniques that we're going to describe provide security. So if you want to secure your traffic over the tunnels, then you need an additional layer of IPsec, for instance, for that purpose. So these tunnels are just connections, so to speak, but they're not signaled. So router to router tunneling, like I mentioned and we saw a few slides ago, is when you're in this example, your two IPv6 nodes are connected to IP version 6 and they need to connect over an IP version 4 infrastructure, so the two routers in between need to establish a tunnel for those packets. Some of the examples of router-to-router tunneling include, as I mentioned earlier, automatic tunnels such as 6 to 4 and 6RD when you're trying to tunnel IP version 6 packets across an IP version 4 internet, or sort of the reverse thing when you're trying to send IPv4 packets across the service provider's IPv6 infrastructure, then we might use DS-Lite. Host to router tunneling. In this example, let's say node A wants to send an IPv6 packet but is only directly connected to an IPv4 infrastructure. So host A is actually an endpoint for the tunnel. Some of the examples of host to router and router to host tunneling: an IPv6 host that needs to tunnel across an organization's IPv4 infrastructure to reach the IPv6 internet. An example of host-based tunnels is ISATAP, which we'll describe more in the second topic. Another example of a host-based tunnel is Toredo if you're running in the presence of a NAT. Host-to-host tunneling is when, let's say, you have two IPv6 hosts that are both connected to an IPv6 infrastructure. They can reach each other directly over the IPv4 infrastructure, so no routers are required, but they need to establish the tunnel to get their IPv6 traffic over an IPv4 tunnel. And again, just like with the host-to-router function, the ISATAP is the most common example of host-to-host tunneling. Implementing IPv4 tunneling for IPv6 then. So there are a variety of overlay tunnels, protocol-based tunnels, IPv6 over IPv4, or possibly even IPv4 over IPv6. So as we talked about earlier, there's a couple different types of manually configured tunnels and various flavors of automatically configured tunnels, whether it's host to host, host to router, router to router, in the presence of NAT or not. So with overlay tunnels, IPv6 packets are encapsulated in IPv4 packets across an IPv4 infrastructure. It allows communication between isolated IPv6 networks without upgrading the IPv4 infrastructure between them. It can be configured between border routers or between a border router and a host. Both tunnel endpoints must support both IPv4 and IPv6 protocol stacks. In other words, they need to be dual stacked. They also have maximum transfer unit issues to keep in mind, as we discussed earlier. And the key thing here is tunneling in general should only be considered as a transition technique toward a network that supports either both protocol stacks or ultimately just the IPv6 protocol stack. And when we say a network, we mean everything: the hosts, the routers, and everything in between. So this slide talks about different types of tunnelings and suggested usage. So we start off with manually configured tunnels. They're the simplest point-to-point tunnels and can be used within a site and between sites. They can carry IPv6 packets only, and that's the key differentiator between that and a GRE tunnel, because GRE tunnels can carry a variety of different types of traffic. Automatic tunnels, so you have what was originally referred to as a compatible IPv6 tunnel, where you had all zeros ending in the 32 bits of the IPv4 address. That's no longer recommended. Obviously, there is no routable portion from an IPv6 perspective. There's ISATAP tunnels, which, just like all automatic tunnels, are point-to-multipoint tunnels, are used to connect systems, in other words, hosts. So they're host-to-host, host-to-router type of tunnels within a site, hence the intra-site designation of the address. And what this allows, ISATAP also allows sites to use any IPv6 unicast prefix. We'll cover that more later. The original form of tunneling isolated IPv6 sites across an IPv4 network was the automatic 6-to-4 tunnel. And as I mentioned earlier, sites use the address prefix of 2002::. But automatic 6-to-4 tunnels are being replaced by automatic 6RD tunnels, and so that allows the sites to use any IPv6 unicast address as opposed to the 2002 prefix. Manually configured tunnels are the equivalent to a permanent link between two IPv6 domains over an IPv4 backbone. Manually configured tunnels are inherently point-to-point between border routers or even between a border router and a host. So therefore an IPv6 address is manually configured on a tunnel interface and in the routing tables, and manually configured IPv4 addresses are assigned to the tunnel source and destination, but manually. In other words, not extracted from the accompanying IPv6 packets addresses. Just like any tunneling technique, the host or router at each end must be dual stack. Manual GRE or generic routing encapsulated IP version tunnels provide a similar point-to-point service and are manually configured, but they are not tied to a specific type of protocol for transport. In other words, instead of just transporting IPv6 traffic, you could also transport other protocols such as ISO protocols as well. So you have an encapsulation of the layer 2 header of the link that you're sending on, the tunnel IPv4 header followed by a GRE header, and in the GRE header it would indicate the protocol that tunnel IPv4 is carrying. And in the case of IPv6, it would be the original IPv6 packet encapsulated following the GRE header. So look forward to part 2 of this presentation, which will discuss in more detailing specific tunneling techniques such as 6RD, DS-Lite, as well as translation mechanisms for IPv6 transition. Otherwise, thank you for taking the time for viewing this topic of the Demystifying IPv6 course on Transition Mechanisms Part 1. Welcome to this topic of the Demystifying IPv6 course on IPv4 IPv6 transition. This topic is actually part 2 of the IPv4 IPv6 transition, so we'll be picking up where part 1 left off. Just a reminder, in part 1 we talked about dual stack or IP layer, DNS infrastructure, and we started our discussion of IPv6 over IPv4 tunneling. In part 2, we'll cover more specific examples of IPv6, IPv4 tunneling, as well as some translation mechanisms. So just a reminder from part 1, there are basically 2 different types of tunnels: configured tunnels, which require the endpoints to be configured manually, and automatic tunnels, where the IPv4 address is embedded in the IPv6 address, and the tunnel endpoints are determined automatically. In this part 2, we'll talk specifically about ISATAP 6-4, 6RD, and Teredo. ISATAP stands for Intra-Site Automatic Tunneling Addressing Protocol and is described by RFC 5214. It is a host-to-host, host-to-router, or router-to-host automatic tunneling technology, so it's always got at least one host at either end. It provides basic unicast IPv6 connectivity between IPv6 hosts across an IPv4 intranet, hence the term intra-site. ISATAP hosts do not require any manual configuration. It's automatic by the protocol stack to create ISATAP addresses using standard address configuration mechanisms. Hosts create a linked local IPv6 address from a configured IPv4 address. So as the graphic below depicts, the IPv4 address is actually embedded as the least significant 32 bits of the host IPv6 address. So an IPv4 address is configured on the host, and it can automatically derive an IPv6 address from that. It uses the next significant 32 bits with the value 0000:5EFE and the most significant 64 bits as the global or local unicast prefix. So as described in this slide, it can configure itself with at least a linked local IPv6 address, or if there's some automatic mechanism, either router advertisements that it can receive or a DHCP v6 server, it can configure its global unicast prefix that way. So ISATAP components are depicted in this slide. It could be just two ISATAP hosts connected to an IPv4 infrastructure. So it could be your own intranet in your own company. And when you turn on the IPv6 stack in the host, if it's a Windows machine, it can automatically derive a link local address based on its configured IPv4 address, even though that IPv4 address might be derived via DHCPv4. And then the two ISATAP hosts could actually communicate directly with each other without any further interaction from the IT department in the company and exchange IPv6 datagrams over the IPv4 infrastructure. As I mentioned before, if there is an ISATAP router connected to the same IPv4 infrastructure, it can announce using router advertisements an IPv6 prefix to ISATAP hosts over the IPv4 infrastructure, and they can configure a global unique routable IPv6 address that way. And then those IPv6 packets that are destined off-net, in other words, even possibly for the IPv6 global internet, can be routed through the ISATAP router. So the previous slides described an intranet solution for automatic IPv6 over IPv4 tunneling. What about a mechanism for doing that over the global IPv4 internet? So RFC 3056, also referred to as 6-4, has described a mechanism for that. Keep in mind that there is a more current method for doing this type of connectivity called 6RD, which we'll cover later on. But let's start out and look at the way it was originally envisioned to do so, and in fact actually did do so for some time. So as this slide mentions, it is a router-to-router automatic tunneling technology. It provides unicast IPv6 connectivity between IPv6 sites and hosts across the global IPv4 internet. It uses a specific prefix of 2002 : followed by the next 32 bits, which would be an IPv4 address, /48, giving you 16 more bits to configure IPv6 subnets, and then of course the last 64 bits was going to be a host identifier. So actually requiring a 2002 prefix is a major drawback of 6-4, hence 6RD. Embedding an IPv4 is its second major drawback. Remember, we're running out of these, so this won't work on a globally wide basis, at least not for the foreseeable future. But it does give a full /48 to a site based on its external IPv4 address. So one external IPv4 address can be used by an entire intranet of IPv6. IPv4 external addresses are embedded in the 2002 prefix as I described above. So the next 32 bits following the 2002, giving you a /48. So another way to express that is a 2002 : the IPv4 address the 16-bit subnet, : /64. So the full 64 address looks something like 2002 : wwxx : yyzz : subnet ID : interface ID. And finally, there must be at least one router acting as a relay between the 6-4 domain and a given native IPv6 domain. So this slide shows you the 64 components in a wider spread basis. I'm going to go ahead and zoom in on various of these components as we discuss this. So to start with, at the bottom, Site 1 is a native IPv6 subnet, although it is a native 6-4 subnet, so the IPv6 prefixes start with 2002 : the IPv4 address of the 6-4 router 1 connected to router 1, which is 11.0.0.1. Now, consider in this example that the IPv4 internet can route 11.0.0.1 and also knows how to reach 12.0.0.1, 13.0.0.1, but again, since it's a global IPv4 internet, it should be able to route any public IPv4 address. So consider a 6-4 host in Site 1 wants to communicate with another 6-4 host on Site 2. And so it will formulate a source and destination IPv6 address using the 6-4 prefix, 2002 followed by 11.0.0.1 for its source, and then an IPv6 6-4 address with 12.0.0.1 as a destination, which are the corresponding IPv4 addresses of 6-4 router 1 and 2. Once those are encapsulated in an IP version 4 address with 11.0.0.1 as a source and 12.0.0.1 as a destination, then that can be routed through the global IP version 4 internet. And in turn, router 12.0.0.1 can strip off the IP version 4 and forward the raw IP version 6 6-to-4 packets from host on site 1 to the host on site 2. Of course, the reverse would hold true back for the reply. Now in this example, 13.0.0.1 is actually a 6-to-4 relay router. And a 6-to-4 relay router is one that has a link into the IP version 4 global internet and a link into the IP version 6 global internet. So it can relay 6-to-4 packets to the IP version 6 internet and vice versa. So again, if the host in site 1 wants to send a packet to a host on the global IP version 6 internet, it would still use its 6-to-4 address as a source, but then it would just use a global IPv6 address as a destination, and the 6-to-4 router 1 would have to know to deliver that to the 6-to-4 relay router 13.0.0.1. And so it would use a source IP version 4 address of 11.0.0.1 and send it to the destination 13.0.0.1. The relay router would receive it, de-encapsulate the packet, and send it to the IP version 6 internet. Now, as you can imagine, there may be some routing issues when we're going from 6-to-4 to the IP version 6 internet and back. So the IP version 6 internet needs to know specifically which relay router and therefore which IP version 4 link to use to get to the appropriate 6-to-4 network and vice versa. So there are going to have to be some manual interaction with the routing protocols, BGP4+ specifically, in order to make that happen. So here we have an example of using the two techniques, both ISATAP for intra-site and 6-to-4 to route between sites over the global IP version 4 internet and even to the IP version 6 internet through a relay router as described before. So locally, the ISATAP hosts would configure themselves based on their IP version 4 addresses with an ISATAP address where the interface ID has the value 5EFE followed by the 32 bits of the IP version 4 address that the host gets, and then the ISATAP router, which in this case is also a 6-to-4 router, will announce a prefix, a 6-to-4 prefix though, that the ISATAP host will use, and then it will combine its 6-to-4 address, the 2002 prefix, with its ISATAP address with the embedded IP version 4 address as the least significant 32 bits. And of course, it's going to use the IP version 4 sides of the IP as also part of the 6-to-4 address. So in the case of 6-to-4 router A, the 157.54.0.1 translates to 9D36:1 and with the prefix of 2002. So when ISATAP host A wants to communicate with ISATAP host B, it can use the 6-to-4 addresses and use that across the IP version 4 infrastructure that they're directly connected to using the ISATAP mechanism of tunneling. But when they want to communicate to the IP version 6 internet, they could also encapsulate those directly over their IP version 4 infrastructure, but then it will be routed through the IP version 4 internet via the 6-to-4 routers and to the 6-to-4 relay routers as previously described. So 6-to-4 worked fine for a while, but the limits were already noted previously. But instead, 6RD was defined by RFC 5569 as a better way. So 6RD refers to IP version 6 rapid deployment on IP version 4 infrastructures. It facilitates IP version 6 rapid deployment across IP version 4 infrastructures of internet service providers. 6RD facilitates IP version 6 rapid deployment across IP version 4 infrastructures of ISPs, not necessarily the global IP version 4 internet. It was, however, derived from 6-to-4, but only operates within a single ISP. RFC 5569 is only 9 pages, so obviously it's a very simple implementation, although it does derive some of its functionality from 6-to-4, so it references to that as well. So a little bit of the history of 6RD. It was first proposed in November 2007, and a service provider in France immediately decided to implement the solution. It was so simple that it only took 5 weeks to implement. The first draft describing the 6RD mechanism and freeze deployment was submitted to the IETF in February 2008. It was then published in January of 2010 as an informational RFC 5569. It was March 2010 that a working group approved that 6RD should become a standards track RFC. In August 2010, the standards track RFC 5969 was published. And finally, in the US, Comcast made 6RD software for home gateway devices available via open source for free, so the implementations took off from there. So the 6RD specification modifies functions of 6-4 to replace the standard 6-4 prefix of 2002/16 by an IPv6 prefix that belongs to the ISP assigned address space, so you no longer have that limitation of a 2002 prefix. Also, the 6-4 anycast address that was used for the 6-4 relay routers that connect to the IPv6 global internet is replaced by another anycast address chosen by the ISP. And that's one of the main things of 6RD is everything is under the control of a single ISP, and it's not relying on BGP updates and other messages to find IPv6 relays, as was the case with 6-4. The ISP then operates one of several 6RD gateways, which are essentially just upgraded 6-4 routers, at its border between its IPv4 infrastructure and the IPv6 internet. So it would require that the ISP itself have a native connection to the IPv6 internet. CPEs would support IPv6 on their customer side and support 6RD upgraded from 6-4 functionality on their provider side. So the actual encapsulation of IPv4 and IPv6 is going to happen by the customer CPE. So before 6RD, so on the upper left you had your typical IPv4 customer premise or CPE and CPE router, and then your ISP IPv4 network, which in general your customer side would have a private IPv4 address, and then on the ISP side of the CPE router you would have been defined an IPv4 public address, and your CPE router would use NAT. And then you would have a carrier router connection to the IPv4 internet. So this is the way that things have operated for years. After 6RD, the CPE router is actually upgraded through software to be a 6RD router and can encapsulate IPv6 packets from the CPE in IPv4 over an IPv4 tunnel to a provider carrier grade 6RD gateway, which itself would have a native connection to the IPv6 internet. IPv4 native packets would still traverse through the carrier router that connected the ISP's IPv4 network to the IPv4 internet. But now, from the customer CPE, we have IPv6 connectivity to the IPv6 internet. (6RD) components and addressing, so you have an ISP IPv6 client, CPE router, the ISP infrastructure over which an IPv6 and IPv4 tunnel can be created, a 6RD gateway, an IPv6 internet, and the IPv6 internet client. So the link on the customer side is actually an IPv6 link, so the customer's client can actually be a native IPv6 client. Across the service provider's infrastructure, the CPE router will create an IPv6 over IPv4 tunnel. There's an IPv4 anycast address that's ISP assigned that the CPE routers knows would be the 6RD tunnel gateway. The ISP's IPv6 clients can use the IPv6 prefix of the ISP, and then the 6RD gateway can just announce a different subnet for each client. The IPv4 address of the CPE router is assigned as the IPv4 address of the customer site, and of course will become the 6RD tunnel endpoint. So notice how the ISP IPv6 client creates a 6RD address using the ISP's IPv6 prefix as well as the IP version 4 address of the ISP side of the CPE router, followed by the ISP client's interface ID. Then the CPE router can make a simple decision. Does it use an IPv4 route to the 6RD gateway, which is the case when the ISP's IPv6 client wants to communicate with an IPv6 internet client, or if it's just another client within the ISP's routing domain, it can use a tunnel to another 6RD CPE. So when comparing 6RD to 6 to 4, with 6 to 4, connectivity to the IPv6 internet is best effort. There is no guarantee that there will be working routes toward the 6 to 4 relay. A 6 to 4 host is not guaranteed to be reachable by all native IPv6 hosts. An operator of a 6 to 4 relay has no control over which hosts use it. Operators also have little incentive to maintain a good quality of service as the traffic grows. However, with 6RD, each ISP uses one of its own IPv6 prefixes instead of the special 2002::/16 prefix standardized for 6 to 4. Therefore, a provider is guaranteed that its 6RD hosts will be reachable from all native IPv6 addresses, and there is no relay server to be used outside of its own control. Therefore, it also keeps full responsibility for the quality of service experienced by its own customers. 6RD also reduces the scope for traffic anonymization attacks such as those possible with 6 to 4. Well, as we switch gears and talk about some more transition mechanisms, let's talk for a moment about traditional network address translation, or NAT. Most of us are familiar with private IP version 4 NAT to public IP version 4. That's also referred to as NAT 44. With it, the service provider infrastructure uses public IP and the CPE only performs a NAT. More recently, we've used private IP version 4 NAT at the CPE to private IP version 4 translation on the service provider's backbone. Finally, somewhere at the edge of the service provider, translate that to a public IP version 4 address. So there you have two actual NATs going on, private to public, or NAT 444. So the service provider infrastructure also uses a private IP, but as a public-facing interface. That enables a larger scale of using public IP addresses with more private clients behind it. However, at the service provider edge, it does require a large-scale NAT solution, or LSN, architecture, since the provider has to NAT to, not just the CPE or home modem. Of course, there can be scaling issues with that. So another technique could be private IP version 4 NAT to private/public IPv6 to an IP version 4 public address, or NAT 464. However, that would require the CPE modem to translate from IP version 4 to IP version 6. And as we'll talk later on in this topic, translation is not always that easy. It also would still require a large-scale NAT to also translate from IP version 6 to IP version 4 at the service provider's edge. So NAT 464 is not considered a very good solution. So what would be the best solution? And this is what we're going to talk about on the next few slides. There's another technique referred to as DS-Lite, where the CPE only has to tunnel IP version 4 and IP version 6 towards the provider, so the CPE doesn't even have to perform NAT. So similar to what we talked about with 6RD and 6 to 4, but in this case we're talking about the CPE being IP version 4 and the service provider's backbone being IP version 6. So now the large-scale NAT only has to perform NAT 44, so just one conversion of NAT. Of course, it would be a tunnel endpoint too, but as we've described, for instance with 6RD, that's just a simple software upgrade. So DS-Lite is defined by a draft DS-Lite broadband deployments following IP version 4 exhaustion. It allows IP version 4 CPE hosts to reach an IP version 4 NAT at the service provider's edge over an IP version 6 tunnel between the CPE modem and an ISP router. It is a better way to share IP version 4 addresses among customers. Public IP version 4 addresses on the internet side of the service provider's edge, not in the service provider's network. It combines two well-known technologies, IP, IP version 4 and IP version 6 tunnels in this example, and network address translation. It also enables both continued support for IP version 4 services and incentives for the deployment of IP version 6. Because if the service provider's backbone is already upgraded to IP version 6, it's a real good incentive for customer CPEs to do the same. So this is the DS-Lite architecture and the terms before and after. Sort of a funny way to refer to it because before is on the home link side, so before we actually do any translations, and after is at the edge of the service provider's network or after we've done the translations that we have described. So the before device is referred to as the basic bridging and broadband element, which is essentially the customer's CPE. And if you remember, as I described a moment ago, the customer's CPE is not required to do any translation, rather just tunnel the IPv6 packets in an IPv6 tunnel. The after gets its name from the address family translator router element. The after, as I described earlier, is a large-scale NAT or LSN. Anytime you have to do NATing at the edge of a service provider's network where it connects to either an IP version 4 or an IP version 6, you can expect there's going to be a lot of connections going through it, hence the term large scale. So I'm going to cover three scenarios for DS-Lite, the first one being existing IP version 4 customer. So in this case, the customer, as you can see at the bottom of the screen here, has a private IP version 4 address of 10.1.1.1, and its CPE is going to just encapsulate the packet over the service provider's IPv6 infrastructure, but not have to worry about doing any NAT. The NATing is actually going to occur when it gets to the edge of the service provider's network, the LSN, which has a mapping between the inside IP version 6 plus IP version 4 source address for the tunnel, and then an outside public IP version 4 address. So it's a simple way to provide connectivity to existing CPEs that are using private IP addresses across the IP version 6 network of the service provider, and then translate it back to a public IPv4 address for connecting to the IPv4 internet. Scenario number 2. So since the service provider's network is already IP version 6, then a customer can add a home gateway that supports both its IP version 4 and IP version 6 protocols. And so IP version 6 native traffic, a client at the customer side can just be configured with an IPv6 address, and then IPv6 packets can be routed through the IPv6 network of the service provider to the IPv6 internet. Whereas IPv4 traffic from the customer would have to be encapsulated and translated as I described in scenario 1. For scenario 3, it is possible for a customer to be dual stacked to run both IP version 6 and IP version 4 traffic and directly connect to the ISP without even using a CPE modem. So scenario 3 would combine both scenarios 1 and 2, 1 for the IP version 4 traffic and 2 for the IP version 6 traffic, but provide the customer a native link into the ISP without even having to go through a CPE modem. So now that we've described some of the most common tunneling mechanisms used today, 6-to-4 to tunnel IPv6 packets across the IP version 4 internet, and 6RD to tunnel IP version 4 packets across a service provider's IPv4 network. Also DS-Lite to tunnel IP version 4 packets across the service provider's IPv6 internet. There are some other tunneling mechanisms out there for more specific types of stuff. So to start with, there's Teredo, which is a tunneling protocol designed to grant IPv6 connectivity to nodes which are located behind IPv6 unaware NAT devices. So it provides a way of encapsulating IPv6 packets within IPv4 UDP datagrams that can be routed through NAT devices and on the IPv4 internet. The Teredo protocol performs several functions. It diagnoses UDP over IP to determine the kind of NAT present. It assigns a globally routable unique IP version 6 address to each host using it. It encapsulates IP version 6 packets inside UDP IPv4 datagrams for transmission over an IPv4 network, which includes NAT traverso. And it routes traffic between Teredo hosts and native non-Teredo IPv6 hosts. There's also the generic packet tunneling in IP version 6, which describes mechanisms by which a packet of a different protocol is encapsulated and carried as a payload within an IPv6 packet. The IPv6 tunnel broker is described in RFC 3053. Tunnel brokers can be seen as virtual IPv6 ISPs providing IPv6 connectivity to users already connected to the IPv4 internet. So for instance, you using your ISP's connection at home, you can find a public tunnel broker available such as GoGo6 to provide you that connectivity. Just Google GoGo6. Some service providers have implemented their own to provide IPv6 connectivity to their customers over their existing IPv4 backbones. One thing about tunnel brokers is the implementations require special application software to be installed on your client. RFC 2529, also known as IPv6 multicast tunneling, has long been deprecated. There's also a variety of translators out there. The idea of translators are to actually rewrite the IP and possibly application layers. So instead of tunneling, they take an original IP version 4 packet and translate it to an IP version 6 packet and vice versa. There have been a variety of different types of translators written, whether they have to work at just the network layer including the transport layer, and also if they need to include rewriting the application layers as well. So a network layer translator called Stateless IP ICMP Translation Algorithm, or SIT, was described in RFC 2765. SIT actually replaces packet headers IPv4 with IPv6 and vice versa. It also translates ICMP messages and fragments IPv4 messages to fit the IPv6 MTU when necessary. Another network layer translator is NAT-PT, but there's a major issue with NAT-PT because it breaks DNS-SEC and therefore has major security issues. Therefore, the replacement for NAT-PT is now called NAT-64 and offers a translation between IP version 6 and IP version 4 in much the same way as NAT-PT. NAT64 is combined with DNS64 to create the complete translation package to allow IPv6 clients to access IPv4 servers. Another network layer translator, Bump in the Stack, is described in RFC 2767 and is where the translator resides on the host and allows IP version 4 applications to run on IP version 6 hosts. Transport Relay Translator, or TRT, described in RFC 3142, is a TCP UDP relay translator and translates both the IP and TCP layers from IP version 6 to IP version 4 and vice versa. As far as application level translators are concerned, Bump in the API is described in RFC 3338 and allows dual stacked IP version 6 hosts to use IP version 6 applications. It has the same goal as Bump in the Stack, but translation is between IP version 4 and IP version 6 APIs, or application layer interfaces, and so therefore no header translation is required. Application layer gateways are necessary when the application layer contains an IP address. Such is the case with SIP and FTP. So application layer gateways have long been used in firewalls and some NATs even for just IP version 4. Thank you for taking the time for viewing this topic of the Demystifying IPv6 course. on IP version 4, IP version 6 transition, part 2.